Assalamualaikum warahmatullahi wabarakatuh. My name is Mohammad Haziq bin Muhammad Anuar Zamani. My metric number is AE190027. So I will present for the introduction and fishbone diagram. Okay, for the introduction, pulse code modulation or PCM is a method used digitally represent sample analog signal. Okay, in a PCM string, the amplitude of the analog signal is sampled regularly at uniform interval, and each sample is quantized to the nearest value within a range of digital steps. Okay, the pulse code modulator circuit digitize an analog signal code and sample it, and then send it as an analog signal. Okay, that's all from the introduction part. We go to the fishbone diagram. Okay, for the fishbone diagram, we have 5 software, measurement, method, scenario, process. Okay, for the software, the causes is software not compliant, fixing error. Okay, for the measurement is accuracy, sampling, frequency. For the method, encode and decode modulating signal, pulse code modulation technique. Okay, for the scenario is a n-bit encoded PCM data, a sampling frequency, and the last one is a process quantization interval voltage range, allowable amplitude modulating in certain range. These are the resulting PCM signal characteristic under different scenario. Okay, I think that's all from me. Thank you.
And hello everyone, so this our design for the part A, part B and C. So this generally for the part A, part B and C. So for the part A, the simplified signal is the 200 already given from the lecturer in here. So 50 for white, and model signal of course is 5, and 100 is from the formula given from the lecturer. So I will run the simulation in here. So as you can see, for the oscilloscope 1 is for the, you can see the process from the sampling to the quantization in here. So from the wave go to the quantization, and then for oscilloscope 2, so from the quantization is go to the process for encoding in here. So it's passed from the encoder in here. So for the here is integer to bit converter is for the 4-bit. So this our result in here. We have, for example, we have 1 1 1 1, and another is 0 0 0 0 in here. So this example I said. So back to here is bit to integer converter in here. So after uniform decoder, process have a decoding in here. From the decoding back to the quantization in here, back to 0 in here, and after sample and whole, they are different in here between this. Okay, then after filter from the quantization in here is back to the wave back, and what we want to see is recovery in here. This input for modulating signal in here. So for the red line is recovery in here. Okay, next, that's all for the scenario 1, and for the scenario 2 is for the 8-bit. So for the 8-bit, it's same as for the first scenario, but the difference is we use 8-bit in here. So we have a 8 wave in here, as you can see. So how to read it? For example, I read it 1 1 1 1, and for the same time in 1, and so 1 1 0 0. So that's example for read 8-bit in here. And next, what I want to see is for the recovery. So recovery also same as before in here, but I've explained at the report. which is that before that I have also for the wave in here. We have a range in here. We have a sign 1111 for this for the 4-bit. 4-bit is 2 power of 4, so we have the 16 here range in here. So 111, 110, so that's how to read it. Okay, next is what I want to show. This result we discuss, and this two sample in here we put. Okay, and of course the recovery, as we can see in here, the highest amplitude is before wave is 5 volt compared to after is 2.1 or the 2.2 volt in here. So the ratio between it, and the reason is different is it is due to incomplete simulation to get the perfect waveform, which is half nearly same as before the PCM process. So that's all for the simulation and for the part A. Of course for the part B, part C is also same, but the difference is we want to change the value in here. For the part B we use 500 in here. For the part C I think we use 50. So that's all for simulation. Thank you.
Okay, now I'm going to present about the part B, which is for sampling for empty is more than required according to Nyquist. So we have the two scenario for this part, which is for 4-bit encode PCM data and 8-bit encode PCM data. So for the first scenario, required sampling frequency is greater than 2fn. So we calculate the sampling frequency here is equal to 500 Hz, and the bit rate is 2 kilobyte per second, and for the bandwidth is 2 kilohertz. And next, the figure of PCM encoded signal in binary form, which is 4-bit encode PCM display. So we have 3 samples here, which is 1000 and 1001 and 1011 for the third sample. And for this sample, we are using 4 bits encode PCM data, which means we have 16 level of quantization. And next, the figure show the PCM encoded signal in binary form at modulating signal, and this shows the converted binary numbers back into the past, having the same quantum level as those in modulated. Next is for the recovery modulating signal. So as you can see, there's a two waveform here. For blue is before the process, and red is after the PCM process. So you can see it shows a slightly difference between two waveform, and the highest amplitude for before wave is 5 compared to after is 3. And the reason for this is because of the difference, maybe due to incomplete simulation to get the perfect waveform, which is have nearly the same wave as before the PCM process. And next is for next scenario is for the 8-bit PCM encode data, and we calculate the sampling frequency 500 Hz also, and the bit rate is equal to 4 kilobyte per second, and the bandwidth is 4 kilohertz. And next is for the PCM encode signal in binary form. We have 3 samples also, which is for first sample is 1000 and second is 1001 and 1001, and for the third sample is 1011 And for this we are using 8-bit, so which means we have 256 level of quantization. And next is for the PCM encode signal in binary form at modulating signal, and the figure shows the passcode modulate convert the binary numbers back into the pass, also having the same quantum level as those in the modulator. And next is for the recovery modulating signal, Same as before. For the blue color is for the before the PCM process, and red is after the process. And the highest amplitude for before is 5, and for the after is only 1. It is also the same reason, maybe due to incomplete simulation to get the perfect waveform, which is have nearly the same wave as before the PCM process. And for the solution is something must be changed or add in the simulation to fix the wave and get a better result. And all those changes will be made in part D to fix the wave. So we have a great waveform compared to this result here. And I think that's all from me. Thank you.
Okay, next we will go to part C. So part C, sampling for empty is lower than the minimum required according to Nyquist. So for scenario 5, we have the sampling frequency for this scenario is lower than 2 FM and number of bits encoded on PCM data is 4 bits. So for the first, we will go to the parameter that we use. The sampling frequency is Fs equal to 2 FM. So for Fs, for the sampling frequency, we have 40 Hz, and for bitrate is 0.16 kilobyte per second, and the bandwidth is 0.16 kilohertz. So for the first, we go to the first waveform, which the figure shows the converted signal into digital form after being encoded through the PCM modulation. For this scenario, the FM is 20 Hz, so Fs is 40 Hz based on the equation that we get from the sampling frequency above. We also using 4 bits encoded PCM data, which mean we have 16 level of quantization. So we could prove that increasing number of levels reduce quantization noise but also increase the number of data needed to be sent. So next we will go to the second waveform. So the figure shows that pulse skirt modulator convert the binary number back into pulses having the same quantum level as those in the modulator. These pulses are further processed to restore the original analog waveform. Based on the table for the quantization range, these figures prove that the 4-bit PCM code is within the range in quantization for 3 samples given. So here is the waveform. So for blue is for before and red is after. So next we go to the last waveform. So from this waveform, it shows the modulating signal after being decoded through the PCM modulation. It shows a slightly difference between two waveforms, which for before we have the blue waveform, and for after waveform we have the red color the process. The highest amplitude for the before wave is 4.8 compared to after the process, which is 2.1 for the highest amplitude. The reason for the differences on the waveform is maybe due to the incomplete simulation to get the perfect waveform, which we could get the nearly same as the wave as before the PCM process. So we could say that this simulation is good. So that's all for part C.
Hi and Assalamualaikum. So I will be explaining for part D. For the first part, based on the initial setting in part B, there are two different amplitudes that need to be used on two different scenarios. For amplitude Vm equal to 15 volt, the result of waveform is as shown as in figure 5.1, and for amplitude Vm equal to 0.5 volt, the result is as in figure 5.2. The waveform shows that there is difference in amplitude of resultant recovered modulating signal is not the same as analog modulating signal for part B and part D. For part B, the analog modulating signal is 5 volt, while the resultant recovered modulating signal is around above 2 volt. For part D, when the amplitude is 15 volt, the analog modulating signal is 15 volt, while the resultant recovered modulating signal is around above 5 volt. While for amplitude 0.5 volt, the analog modulating signal is 0.5 and the resultant recovered modulating signal is around above 0.2. The value of Fs used in both parts are the same, which is 500 Hz, and the value for period is 0.006 second. Thus, this indicates that both parts have the same wavelength. For the next part, we need to suggest a way to make the analog modulating signal is same as the resultant recovered modulating signal. So, we add the gain block, saturation block, and transport delay block. The gain value is set to 1.2. The saturation block is to limit the signal upper and lower boundaries of the amplitude value. The amplitude value that we use is 5 volt. Thus, the parameter of upper limit and lower limit are positive 5 volt and negative 5 volt. When the analog modulating signal falls inside the range defined by the lower limit and upper limit, it is ignored. When the analog modulating signal falls beyond of this limitation, it is clipped to the upper and lower bound. The transport delay blocks delay the continuous input signal of analog modulating signal by the amount of time given, which the time delay is 0.055 seconds. This block can be used to mimic a time delay. The block produces the initial output parameter at the start of simulation until the simulation time exceeds the time delay parameter. The block then starts creating the delay input. The delay block saves input points and simulation times in a buffer during simulation. The initial buffer size parameter specifies this value. This is the outcome of similarities between two waveforms. The waveform of resultant recovered modulating signal, which is the red one, is almost similar as the analog modulating signal, which is the blue one. So, that is all from me. Thank you.
Pikachu!